what we're doing in a meta-analysis is computing a sample size weighted average. That's all it is. And with the weights based on the information value contained in the individual study, and that information value is roughly indexed by the sample size. In this case, because all of the studies have the same sample size, they all have the same weight. Okay. Now, what we care about, to pick up on what I said before about sampling error variance, is we want to know how much the true effects vary. There's only one problem with that. We don't get to see the true effects. We only get to see the observed effects. So the question is, well then how do we know what the variation in true effects is? And pretty much what we do is we know what the observed variance is. That's easy to compute. We know how much variance we would expect based on sampling error. Okay, so we know the total variance. We know the variance that we can attribute to sampling error based on a sample theory. And so then how do we get the true variance? It's very easy. We subtract. So true variance in a meta-analysis is the total variance minus the observed variance minus the variance that we expect based on sampling error formulas. Did I confuse you there? Once again, okay. We care about the true effects, but we can't observe them directly. But we can calculate them, because sampling theory is a very well established part of statistics. So we know how to calculate for any given sample the amount of sampling error variation we would expect. Okay? So based on the samples in our meta-analysis, we can compute how much they should vary from each other just based on the fact that they're from different size samples. Okay? Once we have that amount, we just subtract it from the total amount of observed variance that we actually see in our studies. Okay? So, essentially, think about partitioning the variation into two parts. We observe a certain amount in our data. You can see here that the mean effect varies considerably from study to study, but we can also see the confidence interval basically is a way of capturing the amount of sampling error variance concretely in a study. And this study, although this would be our best guess of the effect, sampling error theory tells us, because it's such a small study, that in fact the true effect might lie anywhere along this line. Okay? When we have a lot of imprecise studies, when we have a lot of studies that are small, and then it makes it very hard to be able to figure out if there's any true variation, because there's so much of the variation that is easy to attribute to sampling error. So it would be hard to conclude that there's really true differences in effects across the studies. When we have relatively precise individual studies, and there's not much sampling error, then it's easier to see when whether there's any true variation in the studies. Now, when we want to know about heterogeneity, in part because it will affect the way we weight the studies. So one of the differences between the fixed effect model and a fixed effects model basically says, I believe there's one true effect underlying all the studies. Okay? In a random effects model, what you're saying is, I believe that there are different true effects, and that these studies in my sample are representative of a larger population of effects. So, in the fixed effect model, our weights are going to be due only essentially based on sample size. Okay? In a random effects model, we have to take into account two types of sampling error. The first is just regular sampling error, and the second one says, well, even though I might have only a small sample, this particular small sample is the only sample I have representing this member of the family of true effects. Therefore, I want to give it some more weight, the way you might want to give a minority group a little more say-so, if you want to reflect the diversity of your population. The weights will change. In a random effects model, larger studies get less weight than in the fixed effect model. And the opposite, small studies get a larger weight in the random effects model than in the fixed effects model. So you can see that in the fixed effect model here, this last study, the intracol study, gets almost 46% of the weight, because that's just based on sample size. However, in the random effects model, even though it still gets more weight than any other study, it only gets about half the weight that it got in the fixed effects model, because we want to give more voice to these other studies who presumably represent a whole family of effects of which they're just the lone representative in our particular meta-analysis. Okay. So T square stands for tau square, which is my favorite index of heterogeneity, and you can think of it as analogous to the variance in a regular primary study. Okay? And tau, which is my real favorite because it makes the most sense to me, is just like the standard deviation in a primary study. So tau is going to be the most intuitively understandable measure of heterogeneity. You would use it to figure out how wide the breadth of true effects is likely to be. So, think about a regular study with a mean and a standard deviation. You can have two studies with the same mean, but if one of them has a big standard deviation, the distribution is going to be a lot wider and encompass a lot more possible values. So, in a meta-analysis, tau is going to be your index of how much the true effects vary using the same metric or the same scale as the mean. So because we change the weights when we have a random effects model, the mean under fixed effect and random effects models are going to be different in most cases. So in this case, we see that the mean for the fixed effect model is a little bit higher than the mean in the random effects model. Okay? And that's because of the different weights given to the different studies. What else do you see about the fixed effect model compared with the random effect model on the bottom? Besides the mean being difference, what else is going on?
Confidence intervals are small.
Okay, so the confidence interval is smaller for the fixed effect than the random effect model. And that's always going to be the case. The mean could be higher or lower in the random effect model compared with the fixed effect model. However, the confidence interval is always going to be wider in the random effect model because you're taking into account the departure of two types of sampling error. So when there's no heterogeneity, in other words, when we're dealing with the fixed effect model, we have to take into account the precision of the estimate around the mean effect. When we believe that there's true heterogeneity, okay, we think that we have two sources of error. Okay, one has to do with the departure of the mean in our sample from the overall mean. The second has to do with the departure of the mean in our sample from the mean of the subpopulation that it specifically represents. Does that make sense to everybody? Yes?
Can you repeat what's wrong?
Okay. When we have no heterogeneity at all, when they all represent one population, the study means vary each from the other just because of sampling error variability. But there's only one source of sampling error variability. It's the departure of each observed mean from the true mean in the underlying population. Does that make sense? Okay. When there is actually true heterogeneity, our overall mean represents an average of different true means, where each of the studies has two sources of variation now. One is the difference between the study mean and the grand mean, and the other one is the difference between the study mean and the true mean of the population or the subpopulation that we drew it from. Okay? So again, in the random effects models, we're saying that we actually have a family of true effect sizes in our meta-analysis, and that they are essentially drawn from a larger distribution of possible true effect sizes that we could have had.
Can I have a question?
Please.
Because now, one question will happen. If you have two different true effect sizes, why do you want to metalize them to get one? If they're really representing two different ones. Because the meta-analysis will give us one, so it's...
Well, that's a very good question. And the truth of the matter is that if you're willing to say, I'm sure that these represent different populations, I wouldn't want to combine them and draw any overall inference, then I would say fine. Don't meta-analyze them. Wait till you accumulate enough studies for each of those populations before you do an analysis. On the other hand, if you're going to draw some overall conclusion about whether a treatment works or not, I would still say that you're better off using the meta-analysis and quantifying the uncertainty in your estimate rather than just saying, oh, it looks like overall it works or it looks like overall it doesn't work. I think that often when we meta-analyze a a small number of studies, and particularly when they do vary in real ways, we're almost misleading ourselves because we're not paying enough attention to both the heterogeneity and the uncertainty in our estimate of heterogeneity. Period. New sense. Nevertheless, I still feel that any time we feel compelled to come up with some overall bottom line, that meta-analysis is still less misleading in that situation than any other way, unless the bottom line is we don't know yet. Does that answer?
No, yeah.
Okay. So I think the main reason that we really want to be careful about heterogeneity, though, is not for statistical reasons, but because we want to make sure that before we draw, recommended treatment or recommend against a treatment, we don't only focus on the mean, but we also focus on the degree to which reactions vary, in the study. Okay. So in this particular study, it looks like it's unlikely that this treatment is going to have, let's say this is help and this is harm. It's unlikely, given the means and the confidence intervals, that it's going to harm anybody. But still, there seems to be quite a big difference in how much it's going to help. Okay, in some cases, we could see in this case, for example, that although it helped in 3 of the studies, in one study it had no impact whatsoever, and another study it was actually harmful. Okay, so maybe for those of you who still are puzzled, maybe this will be a better way of explaining the difference between the one true effect and family of different effects. So if you remember, when there was a consistent effect, all we did was affect the precision of the mean effect, and it got smaller and smaller. If we have heterogeneous effects, even if we had a zillion studies, we would still have a larger confidence interval, because the confidence interval captures the true differences between studies as well as the actual precision of the particular estimate of the mean. So think about, let me see if I can rephrase it again, because I see I'm not being totally clear. When there's heterogeneous effects, what the mean represents is the average effect of a family of effects. When there's a fixed effect analysis and the effects are consistent, the mean represents the one true effect. So, and that's only going to be influenced by our sample size. Okay? You have a question?
Yeah, I have a question. If you see a lot of heterogeneity between your studies, how would you think? I mean, would you first try to find the source of that heterogeneity and then apply a fixed effect model, or you would just say, okay, there is a lot of heterogeneity and then I'll apply a random effect model?
Well, I like to use the random effects model all the time, because if you really don't have any heterogeneity, essentially the random effects model reduces to the fixed effect model, so that there's no real penalty for using the random effects model. What I worry about is when people do a Q-test or a chi-square test for heterogeneity, and they find that it's not significant, and then they say, well, there's no true heterogeneity, and then they used a fixed effect model because it's simpler and neater. Because just like any test of significance, you can have conditions of very low power, and particularly if you're dealing with a meta-analysis where your sample size is the number of studies, you're almost definitely going to have not the power you would want to detect true differences between effects. But what you can do, if you're doing subgroup analysis, is use a mixed effect model where you think that where you basically treat the mean of each group as a fixed effect, but within each group, you use a random effects model.
Within each group as you would use random effect model.
Well, each subgroup, it would, more technically, it depends on the nature of your subgroups. But let's say you're doing a gender analysis. You're doing a subgroup analysis by gender. I know these days, like, there's this whole thinking that gender is a continuum and we have to take into account gender non-conforming people and trans people and stuff like that. But putting that aside for just a minute, and thinking about the traditional way we divide our gender into male and female, those are fixed groups, right? Anytime we sample, they're going to be those groups. So we can treat maleness or femaleness as a fixed effect, but then within the female subgroup, we might have some random things going on, and within the male subgroup, we might have some random things going on. So just as you have more and more true heterogeneity across the studies in your meta-analysis, the mean effect is going to be pulled in the direction of the smaller studies and a little bit away from the direction of the larger studies because of our reweighting. Let me talk a little bit about how the various indices for heterogeneity. I think that would be more useful than going through the slides with formulas. So first we want to isolate the true heterogeneity or the true dispersion, as I said, and that's the question of taking the total observed variation and subtracting out the amount we would expect due to sampling error, and then we have to take a look at what's left. Okay? So to try to visualize what I was talking about before, what we'd really like to be able to see if we had one true effect is this. This In fact, because of sampling error, we actually see something like this, right? So the question is this due to sampling error, or is it likely that there are actually true differences between these studies? We can't know that until we look at the precision of each of the studies. Okay? So if the studies are very imprecise, each one, then it's likely that all of the observed dispersion is due to sampling error variance. Okay? Compared to that, where we have very precise estimates for each individual study, and it's easy to see that the variation due to sampling error doesn't account for the lion's share of true variation across the studies. So we compute the variance of observed effect, okay? And then by subtracting out what we expect due to sampling error variance. What's left over is the true dispersion. Okay? So, if we have very wide confidence intervals, start here. If we have very wide confidence intervals, there's going to be, most of the observed dispersion is going to be attributed to sampling error variation. If we have very precise estimates, then if we have a lot of observed dispersion, we'll know that it's really due to true differences between studies. Okay? So again, very wide confidence intervals means that statistical theory essentially forces us to say, well, most of this is due to sampling error variation. As a scientist, I believe in parsimony. That's certainly a more simple explanation than any substantive explanation that I can come up with. I can only say that true dispersion is going to be what's left over after sampling error variation is taken into account. The less sampling error I have, or the less sampling error I expect, the more I'm able to say, you see the dispersion that I found, it's due to true between study differences. When we have very, very precise effects, okay, then almost all of the dispersion is available for us to say is due to true study variation. When we have very imprecise effects, sampling error variance is going to suck up most of the variation, and there's going to be very little left over for us to try to model by looking at substantive or methodological covariance. We can do a Q test based on the amount of dispersion we would expect given the number of studies we have and the size of those studies. Okay? And Q minus the degrees of freedom. Q is the observed variation. The degrees of freedom tell us essentially how much sampling error to expect, and what's left over, the residual, would be the true standard deviation. There are essentially 5 different indices of heterogeneity that would be useful for you to know about. The Q minus DF is essentially just the basis for everything. The p-value, which is going to test the statistical significance of the variation across studies. Tau, or T, is the standard deviation of true effects, and it's directly analogous to standard deviation in a primary study. Tau square is just the variance, the standard deviation squared, and I square is, which has become the most popular used index of heterogeneity, just tells you the proportion of the total variance that can be attributed to true study differences. Okay, and as a proportion, it's a kind of relative value. And I hope that I'll be able to explain to you why I like tau better than I square as a measure of heterogeneity, although I square also has its uses. Okay. So the p-value basically says, can we conclude that the variation across studies that we see is due to chance or not? Same as any other type of test of statistical significance. So that will depend on how precise the studies are and how much variation can reasonably be attributed to sampling error. I-square answers the question, what proportion of this observed variance that I found is actually true between study variance? So not if the p-test, if the p-value asks, is there any actual true between study variance? I-square says, how much of the variance is true between study variance? Okay? So not from is there any or is it or not to how much of what I see can be attributed to differences, true differences between studies. Okay? So, again, it matters on the amount of observed variance, right? So, if you have a lot of variance, if you have a lot of sampling error variance, then even if you have a certain amount of true variance, it's only going to look like a very tiny amount when you look at I-square. Okay? When you have very little sampling error variance and the same amount of true variance that you had up here, I-square is going to look a lot larger. So, if you I-square is going to depend not only on the amount of true between study variation that you have, it's also going to depend on the total amount of variability you have. So that it's, paradoxically, it can look like you have less true variation in a study with a lot of sampling error variance than if you had been able to do the same studies with bigger sample sizes, and then you would see that they're really, the noise of sampling error doesn't get in the way of your ability to see the true between study variation. Okay? Heterogeneity again puts things on the framework of a normal distribution and puts things in the same metric as whatever you're using for your effect size. I want to just remind you again that I-square is not an absolute measure the same way when we were talking about relative risks versus risk differences. I-square is a relative measure. So you can have the same actual amount of true between study variation, but when you look at it as a proportion of total variation, it could look very different depending on the context. You would only want to use a fixed effect model when you believe that all of the studies are essentially equivalent to each other. So for example, if you're a pharmaceutical company and you're trying to test a new drug, and because of the limitation in physical resources that you have, you can't run 1,000 patients all at once. So you divide them up into 10 samples of 100 each. But they're all drawn from the identical population, they're all treated in the same protocol, they're all treated in the same facility, and so forth. In that situation, it would be legitimate to use a fixed effect model. In most situations, I would argue that it is not sensible to use a fixed effect model because there are going to be enough differences between or across the studies in the way that they were done to make them vary in at least some random ways that could affect the effect size. And in a fixed effect model, essentially, if you do a fixed effect analysis, you can't generalize it. You can only make a summary statement on studies just like the ones in your analysis. In a random effects model, because you believe that essentially the studies in your sample are representing, the studies in your meta-analysis are a random sample of a family of true effects, you can, with more confidence, generalize to studies that might differ somehow from the exact characteristics of the studies in your sample. But even then, let's say you were doing a meta-analysis of studies that were based on people between 40 and 70. You might feel comfortable making some generalizations, but you wouldn't want to then generalize to children because you have no samples with children or no samples with really geriatric patients in your sample. So even though maybe your meta-analysis had a sample of people of 45 and 2 samples of people in their mid-50s and 3 samples of people in their 60s, and you didn't observe all of the ages between 40 and 70, you might generalize within those parameters because you sampled from that range. But you might not want to generalize outside that range. Anna?
So if you have a case when you have consistent effects in several studies, and you have additional study that looks like an outlier, would you remove that study as an outlier, or you would conclude there is random effect?
That's a good question. In general, unless it would be pretty apparent to everybody that that outlier was due to some like transcriptional error, like it's 4 standard deviations difference in a range that nobody's ever seen before, I might be willing to exclude it as an outlier. But except for really odd situations, I'm much more comfortable saying, no, it's a constellation of covariates coming together, producing that effect, and I'd rather treat it in a random effects model. Well, I hope that's the answer you want to give. Lara.
When we get protocols quite often at the Cochrane group that I work for, they often write, we will use the fixed effects model unless we see that there's heterogeneity, and then we'll use random effects model.
Yeah.
And I try and write back and say, I think you have to think more about what you will expect rather than...
Exactly.
But I find they don't...
They don't listen.
I just don't know how to well explain it. Yeah, I don't think I'm explaining it very well, maybe the reasoning. But this is more helpful.
I think that your model always has to be based on plausible beliefs about your sample. And I think that in most cases, it's just very implausible to think that they're all going to be functionally equivalent. Unless somebody's asking a very narrow question and they're fortunate enough so that enough primary studies were done in that very narrow range to be able to meta-analyze that. But in the real world, unless you have some wonderful multi-site study where you're looking at all of the studies separately from the individual sites, but pretty much everything was controlled, that's just not the way things are in the real world. Dosage varies, patience varies, implementation fidelity is likely to vary. There are just too many things going on. And like I said, with today's software, even RevMan, there is no penalty for using the random effects model, because if you really don't have significant between study variability, it basically reduces back to the fixed effect model. But your danger in using a fixed effect model when you should be using a random effects model is that your mean effect could be off, that you're not going to properly weight the studies, and you're going to believe that your estimate is more precise than it really is. Plus the fact that then what makes me crazy is when people use a fixed effect model and then do subgroup analysis or a covariate analysis anyhow. I mean, you can't have your cake and eat it too, right? I mean, if you really think that they differ, then you have to do a random effects analysis, and you want to get a gauge on how much, you know, how much heterogeneity there really is, rather than just saying, well, unless it smacks me in the face, I'm just going to pretend it's not there. So, I think that, Michael thinks that, Julian thinks that, you know. I think even people like Joseph Lau, who used to say, no, I think that as a clinician I want to answer the question for my patient, so I want the meta-analysis to be narrow and I want to use the fixed effect model, has come around to believing that that's sort of like his what he would prefer to see, but that the real literature generally doesn't support that. And it's better to try to accept the heterogeneity as being there and then trying to model the part that's real.
Mm-hmm. I see it more in study in reviews of, say, drugs like a biologic in a defined population like rheumatoid arthritis, and they say, well, the inclusion-exclusion criteria for participants are going to be really quite strict. These new drugs are used in very similar dosages across populations, and then, I don't know, but I still think that they're doing these multi-center studies that are around the world.
They're right. I mean, there are too many. I think there are just too many reasons that things could have differed in some way that you might want to know about for your clinical practice. So, and it's better to look for something and not find it than pretend it's not there when it might be. But okay. If everything comes out of one lab, maybe, you know, you could argue that that would be okay. But,
Can I ask a question?
of course.
In genetics, we usually do also fixed and random effect model, and then we compare between two. And then also, well, we look at the heterogeneity value for, and also do the random effect models. Even if the heterogeneity value is okay, it's fine, it's zero. And then we compare, and sometimes, and usually, it will be very similar result. If it's very different, then we try to figure out why it's very different. So I guess doing two tests, always doing two tests. It's just, and then try to see if they do go in line together, or if there's a difference, and then try to understand why there's a difference. That may be a way to go.
But I'm not sure why you would want to do a fixed effect model if you think that a random effect model applies. I mean, which are you going to believe if they differ?
It depends, because we do a set of genetic variants, and for some genetic variants, because we do one test for like 100 variants, and for some, the true effect will be one in whole population, and for some there will be several. So we don't do 100 tests for 100 genetic variants, but one test for 100, and then it's easier to do one fixed effect for 100 variants and one random effect for 100 variants and see the difference if there is. We usually go for fixed effects. If we do, for example, Caucasian population tests in Caucasian populations, so if they're standardized by population, because we believe the true value of genetic value, true effect would be the same.
I don't know that much about genetic meta-analysis, except that people end up often doing a lot of tests and capitalizing on type 1 errors when they do like genome-wide kind of association tests, but it sounds like you're doing something different.
No, it's the genome-wide association.
Yeah.
Okay. And then prioritize for
Yeah. So, okay, but different disciplines sometimes develop different conventions of how they go around about doing things. But okay, so I think other questions? Okay. So I think I mentioned this already, that in a fixed effect model, you believe there's one underlying true effect, and that so the summary effect, or the mean overall effect you get, is not just the mean, it is the true value in the population. Okay, in a random effects model, you believe there's a distribution of true effects, that the studies in your meta-analysis are a sample drawn from that, and therefore your mean overall effect in your meta-analysis represents a weighted mean of the distribution of true effects. And then, and of course, you want to be careful when you have a lot of heterogeneity. You want to be very careful about interpreting that mean and let it serve as a standard for the whole distribution. So the important things I would like to highlight about the differences between a fixed effect and random effects models are that the meaning of what the effect, the mean effect, or the overall effect is different under the two models. In one case, it represents the best estimate of the single population value. In the random effects case, it just represents the mean of all the values in the distribution of true effects. In the random effects model, the weights are adjusted to take into account the fact that each study sort of brings something unique to the table, and it's not just estimating the overall mean. That the confidence interval is wider because we're acknowledging that we have less precision in the estimate when we're using a random effects model, and that usually the p-value will also vary along with the confidence interval. Okay. You have less power to detect a significant effect in the random effects model, again, because we're taking into account two sources of uncertainty. Some people like the fixed effect model because if they use statistical significance testing, they're more likely to get a significant effect if they use the fixed effect model. But it's answering the wrong question. Okay. So just here's a little thought experiment. We have 4 studies, each with a sample of 1 million. And the true mean effect is 0.5. What would the forest plot look like under the fixed effect model versus the random effects model? And what would the little summary diamond at the end look like in the fixed versus random effect model? Okay? And the fixed effect model, essentially, okay, you have each point estimate with a very tiny confidence interval to begin with, and a summary effect that's practically a point estimate because the confidence interval is so narrow with a sample of 4 million. Okay? In the random effects model, if the studies still can have the same exact mean, but if they really come from different populations, you could still get the same mean with each of them representing quite different true effects. Right? So the mean is the same, but you have a wide confidence interval around the mean to let you know that the estimate of the mean is not precise, and to let you know that it's not a very good estimate of any of the contributing studies. Okay? So even with a sample of 4 million, if we have enough true heterogeneity, we're still going to have a wide confidence interval because we need to reflect the variability in the true effects. So that sampling error variance is contributing virtually nothing to that confidence interval, but it's still pretty wide. Okay. Do not base the model choice on the test of heterogeneity. It's just a bad thing to do. The only legitimate criticism that you might hear about the random effects model is that we don't actually know the shape of the distribution that we're sampling from. Like, we're assuming that it's a normally distributed family of effect sizes, but we have no actual evidence or any even good theory to claim that. You can, if you really believe that in terms of your particular data, you can use the fixed effect model, but interpret it differently. In other words, interpret it just as being the summary of the information from these studies. So in other words, interpret it as a set of descriptive statistics, not inferential ones where you're generalizing to any larger population. So if, and then I'm not quite sure what you do with that information as a clinician. Okay. The last thing that I want to mention is something called a prediction interval. It was developed by Julian Higgins and based on, and similar to something called a credibility interval, which was developed by Hunter and Schmidt. They're both rooted somewhere down the line in Bayes, but essentially what you're saying is if you're using a random effect model where you believe that there is a family of true effect sizes, that besides the precision of the mean effect, you also want to know something about the width of the distribution of effects. Because the confidence interval around the mean doesn't capture all of the variability in true effects in the whole distribution. So the predictive interval, or prediction interval, helps you clarify the difference between the mean, the precision around the mean effect and the actual amount of true dispersion across the whole distribution of individual effects. Okay? And so if this is the confidence interval around the mean, the predictive interval says that the actual dispersion of all the true effects is wider than that. Okay? So just to differentiate, the confidence interval is a measure of precision. It has to do with the mean effect only. It's similar to a standard error. Predictive interval is actually a measure of the whole distribution of effects. It's analogous to the standard deviation of true effects across the distribution, and it really makes sense only when you're using a random effect model. Questions?